All right, so last time we were working on the set of rational numbers, and we are at example 7. And on example 7, well, let me just take one step back. One of the things we talked about last time was this idea of being able to reduce a fraction. And if you'll remember, that was early on in the lesson. Flip back if you would. There was theorem 6.1. I believe. Yeah, theorem 6.1 is the equivalent to talking about how to reduce fractions. You guys remember that one? Where it says if there's a number that you can multiply on top and bottom, it will keep the fractions equal. Likewise, you can reduce them in the same way. Well, this is a similar kind of question to that. So we've got a student, and a student simplifies the fraction m plus n over p plus n into m over p. And the question is, how would you help the student? So those of you who've had one of these kinds of classes with me before know that when you encounter a question like this, it says, how would you help the student? The first thing that you have to figure out is what they're doing wrong and what they're thinking about that might be right. Okay, they've got something that they're thinking about wrong, but from the perspective of something that is right. So what are they doing? Well, the addition's there. So like the problem starts out like this. So they see the number n on the top and the bottom, and what are they doing with it? They're canceling it. Now, is that an operation that exists somewhere? Yeah, we're allowed to do that, but we're not allowed to do that in this case, right? What is it about this case that makes us not able to do that? It's the addition, okay? So you should be able to look at this and figure out, oh, that's not right. It's because that addition's going on, right? So we can talk about that and we can write that down, that the student is, so how do you help the student? Well, first of all, you're going to have to let them know that they're thinking about something right. So this process would work if it were multiplication instead of addition. That's good, because that way if you tell the student what they did right, they don't feel like that they're just always making mistakes. I mean, they did make a mistake, but it wasn't completely out in left field, right? Left field, right? I didn't mean to do that, but All right, so the first thing is that they have some right thoughts. So we might say something like this would work if it were multiplication instead of addition. Okay, so that's a true statement, but it may not mean a lot to the student, because they might say something like, well, why wasn't it going to work for addition? Or how do you know it can't work for addition? So what's one way that you could show them or tell them why it wouldn't work for addition? You could do a number example, okay? So in order to work this out in a number example, I need 3 numbers because there's 3 letters here, right? Okay, so what do you want to let your letters be? What do you want to let m be? 2. What do you want to let p be? 3. All right. What do we want to let n be? This is the value they think they're canceling. 4. All right. Sounds good. Okay, so in reality, we now have 2 plus 4 over 3 plus 4, which actually equals what? I mean, really, what does it really equal? 6 over 7. This is really equal to 6 over 7, okay? Now, if we do what the student tried to do, what they tried to do is they tried to do this, right? And if they had, and their result would have been what? 2 over 3. Okay, so now what? I mean, this is the example. You can't just write this down for the student, maybe. You need some words to go along with it. So what would your words say?
It doesn't match.
Yeah, they don't match. I mean, that's the key, right? And not only do they not match, but you can't change one into the other one. There's no way to reduce one to get the other one out of there, or to multiply one and actually achieve the other result. So these are not equal fractions. So reducing, that doesn't look like reducing, but pretend. Reducing with addition involved. It doesn't work. Does that make sense? That's going to mean a lot more than you just saying it doesn't work. Actually showing an example where it doesn't. Do be careful when you have examples like this, because every now and then you might randomly choose numbers that actually make it work. Just be careful. So if that happens, try another set of numbers, because it's probably not going to happen twice. All right, so you're probably going to be able to find something else that's not going to work if it really doesn't work. All right, we have one more example to take a look at. Example number 8. This says, if we take a set of numbers equivalent to 1 over 3 and graph them as pairs on an xy axis, so that the numerator becomes the x coordinate and the denominator becomes the y coordinate, what type of graph would we get? So the question sounds really wordy, and it's really not that complicated. The first thing you notice that it's talking about is a set of numbers equivalent to 1/3. So that's where I want to start. We would like to write several numbers that are equivalent to 1/3. So what's another fraction equivalent to 1 over 3? 3/9, okay. What else? 4/12. Can I go smaller? I don't want to get too large because it'll make it harder for me to graph. 2/6, okay. And I'm going to do one more that you might not have thought of, just because I want to have some negatives involved to see what would happen. So what if I do -1 over -3? That would work too, right? Okay, so these are equivalent fractions. It says we're going to graph them as points on an xy plane so that the numerators are x and the denominators are y. So if you think about setting up like an xy chart, all the numerators, and I'll just go straight across the top, are your x values. So 1, 3, 2, -1. The denominators, again in order, would be 3, 9, 6, and -3. Is everybody following along so far? And then it says, what are we going to do with that? Graph it. We're going to graph that. All right, so I need, actually, let's see if I can do this. I don't know if this is going to work or not. No, it doesn't look like it. Never mind. All right, so I need to go out to 3 and up to 9. And we're going to plot these points, at least as best we can. So I've got 1, 3. I've got 3, 9. I've got 2, 6. And I've got -1, -3. Okay, so this isn't going to be terribly convincing because it's not terribly accurate. But what should this look like if it were accurate? It should look like a line. Okay, well, that's not too bad. Something like that is what it should look like. There's an exception to it, though. So let's first of all write down what we think this is. This is a line. What kind of graph would we get? This is a line. You can probably figure out the equation for the line pretty easily. Do you know what it is? Or how would you describe it if you didn't want to write an equation for it? I mean, I can draw.
Y equals 3x.
It is y equals 3x. So, Leah, let me ask you then, what is this 3 in this equation representing?
This represents the denominator.
Well, it's coming from the denominator, but that's not what it represents in the equation. Does anyone else have an idea? It's
The
this.
denominator
this-
is
it's
3
this-
times the numerator.
Thank you, Leah. It's the slope. That's what I was looking for, right? It's the slope when we just talk about the line itself. So this is the slope of the line. It's how steep the line is. And we can count it between a couple of our points. So if we took the point 1, 3 and go up to 2, 6, we rise up 3, we go over 1. So this is a slope of 3. So if you didn't write the equation, that would certainly be acceptable too, but you could say it's a line with slope 3. Okay. Now there is an exception to what I just wrote down. This information won't give me a line exactly. There's something on this that needs to be changed. Any idea what it might be?
Would it be positive? Or does it?
Would what be, say that again for me, Angela?
I was just thinking, would it have to be like a positive or a negative?
Would it have to be a positive or a negative? Say, what do you mean by that?
Like the 3, like with the slope of a 3, would it have to be
This
positive?
3 is a positive 3. If you don't put positive on there, it's understood to be a positive, but you can clarify if you'd like. It's just positive simply because we're moving uphill as we go from left to right. Yeah. Did you have an idea, Abby?
I was thinking, like, if you start at 0 and you're trying to get to the 1, 3, if you just go up 3, then you're not at 1, 3, you're at 0, 3.
But if it's you up 3 and over 1, because the slope of 3 is understood to be the same as the number 3 over 1. However, you made mention of something, albeit inadvertently, it sounded like. You said if you start at 0, the origin's what you're referring to, right? Can I start at the origin with this description? What is the ordered pair at the origin? 0, 0. Can I put that in this table? Why not? Because 0, 0 does not equal 1/3, does it? So everywhere else along this line is fine. The ratio is 1 to 3 or 3 to 1, depending on your perspective. But the origin can't be included because it does not have the ratio 3 to 1 or 1 to 3, right? It'd be 0 to 0, and that's not even defined. So this actually has the exception, and there's lots of ways to do it. But one way to do it, that's not done well, let me use a different color, is to say that there's a hole in the graph with a slope of 3 and a hole in the graph, or you could say the origin is excluded, or we can't include the 0, 0 point, something like that. Because that is the only point along here that does not have the desired ratio. Does that make sense? Because that's where these points came from, and it works for every other value, but not at x equal to 0, which gives us that y equal to 0. Okay, any questions? All right.